the oxymercuration-demercuration of an alkene. So we can see in this reaction that it is a reaction that starts with an alkene and the product is an alcohol. This reaction is not in your textbook, but it is in most other sophomore organic chemistry textbooks. And so I like to cover it because it's something you might see on, say, an ACS exam or an MCAT or something like that. Yeah, so it takes an alkene and makes an alcohol. We can see that in doing so, the hydrogen has added to the less substituted carbon atom of the alkene. So this is a Markovnikov addition of water. It's following Markovnikov's rule. So right now it kind of looks like the reaction that we saw. There was the acid catalyzed hydration of an alcohol. The big difference here and the advantage to using the mercury is that it prevents the carbocation from rearranging. So this is really the only case where you would use this reaction with mercury is if you have a product that you want to form that if you didn't use the mercury, you would get a rearrangement. If we didn't use the mercury, we wouldn't have our alcohol at the secondary carbon, it would be at the tertiary carbon. Okay, so you don't need to know the mechanism for this reaction, but I'm going to show you a little bit of it just so you can kind of understand what's going on. So the mercury acetate looks something like this. And it can dissociate so that you end up with a mercury with a positive charge and an acetate ion. Okay, and this mercury with a positive charge is a really powerful electrophile. So this is an electrophile. Okay, so if this is an electrophile, we can expect that our alkene, which we know is a nucleophile, will react with that. So here is the alkene, and I'm going to draw the electrophile. There it is. Okay, so our alkene attacks the electrophile. The electrophile adds to the least substituted carbon atom in order to give the more substituted carbocation. So we have initially this sort of intermediate. Now mercury, if you look at where it is on the periodic table, it's a really large metal. It's got a lot of outer electrons. So I'm just going to draw in one of those pairs. And being a large atom, it can bridge this molecule and essentially lock that carbocation in place. That's what prevents that carbocation from rearranging because you don't actually have a carbocation. You have this bridged mercurinium ion instead. Okay, and so the mercury is helping to stabilize that positive charge. The positive charge is being shared with this mercury and both of the carbon atoms that it is attached to. One of those carbon atoms is primary, the other is secondary. We expect that the secondary carbocation is going to have a little bit more of a partial positive charge than the primary carbocation. So the water that is in solution, which is a nucleophile, is going to attack the secondary carbocation, or carbon with the partial positive charge, rather than the primary carbon. So the water can attack, and we break open this bridge. And we have something that looks like a protonated alcohol. We've still got the mercury hanging on there. That's not going to go away until the second step of the reaction when we add the sodium borohydride. For now, we're going to deprotonate to get to the neutral alcohol at this carbon. So water being a solvent, you have a lot of it. We can see water acting as a nucleophile. Here we can see it acting as a base and removing one of those hydrogen atoms. So then we have the alcohol and the secondary carbon, and and we've still got the mercury attached to this molecule. If our goal is to get a neutral alcohol, we want to get rid of that mercury, and that is accomplished in a separate step of the reaction where we add in sodium borohydride. So we're not going to show the mechanism for this. I'm just going to indicate that you add the sodium borohydride. That mechanism is actually not completely worked out. We're not sure as chemists how that works, but we do know that it does, and we get rid of the mercury and we end up with a hydrogen there. And so the product is that secondary alcohol. The mercury has stopped a carbocation rearrangement so that we don't end up with the constitutional isomer or the alcohol bound to that tertiary carbon.